In this statistics section, we will be discussing the binomial probability distribution, methods for finding probabilities, easy methods for finding means and standard deviation of a binomial distribution. Going to be a whole bunch of different aspects, different examples. We're going to use technology, we're going to use tables, so you're going to see a lot of different stuff going on in this section. All right, so a binomial probability distribution results from a procedure that meets the four following requirements. Number one, there has to be a fixed number of trials, and each trial is going to have a single observation. Each trial must be independent, and again, we've discussed this before, but remember, independent means that the trial before does not affect what happens in this trial, so they've got to be completely independent from each other. Each trial must have all the outcomes classified into two categories. It's either considered a success or a failure. That's it. You can only have those two categories. Hence, they call it binomial, because there's only two things that could happen, success or failure. And the probability of a success remains the same in all the trials. It's not going to change from trial to trial. So little bit of notation for this section. So the probability of a success, we're going to call little p. The probability of a failure, we're going to call little q, and that's just 1 minus p. We'll tell you what q is. N is that fixed number of trials. So our x is still going to be the specified number of successes, 0 successes, 1 success, 2 success. And the p of x is still going to be the probability of getting exactly x many successes amongst those trials. Couple words of caution about this. The word success here is very arbitrary. Success could mean that it doesn't work. So you have to be very careful about how you word things, and you have to pay attention to what a success actually means. And when you're doing a binomial probability distribution, always be sure that your x and p are consistent in the sense that they refer to the same category being called a success. So again, that goes back to your wording, like what does success mean in the context of this problem? So keep that in mind. All right, so let's start with an example. We're going to talk about cash. So an adult smartphone owner randomly selected with replacement, there is a 0.05% probability that that person is cashless, meaning they do not carry cash. Everything is electronic. I know more and more people are moving towards this. Okay, so we want to find the probability that amongst 10 randomly selected adults, that exactly 2 of them are going to be cashless. Now, before we actually go through all of that, let's discuss, like, does this procedure that they just described result in a binomial distribution? Okay, so that's our first question. So let's think about this. So, okay, number one, do we have a fixed number of trials? Yes, we do, because they said specifically they're going to do 10 randomly selected adults. So that's good. We have a fixed number of trials. Okay, number two, they said they're randomly selecting them. So that means that each trial, each adult we choose is not going to have anything to do with the other one. So they're going to be completely independent of each other. So that's good. Number three, each of those 10 trials, is it going to have exactly 2 different outcomes that could happen? And that is true. Either they will be cashless or they will not be cashless. Okay, so, and remember, success is that they're cashless. A failure would be that they are not cashless. And then number 4, we have number 4. I keep forgetting number 4. What was number 4? All right, number 4. The probability of each success remains the same. Yes. Okay. So because there is a 5% chance each time that we randomly choose. Okay. So this is good. Whew, I always forget number 4. Okay, in this procedure, what does result? If this procedure does result, identify the values n, x, p, and q. Okay, so n, of course, is the number of trials, right? So we are doing 10, right? 10 randomly, so n is going to be 10. All right, x is going to be the outcome that they want. In this case, it's the fact that there are exactly 2 of them are cashless. So in this case, x is going to be 2. The probability of a success means the probability that they're cashless, and that's 0.05. And then Q would be a failure, which is that they're not cashless. So if there's a 5% probability that they are cashless, there's a 95% probability that they are not cashless. Okay, so very important that you really talk your way through these and make sure that you understand. And again, just a word of caution about that consistent notation, right? Know what a success is. Like, what are 2 successes? They are cashless versus not cashless. So please just make sure that you're being consistent in your verbiage, because that's very important in these things. There is another thing that you can look at is when you have when your sample size is no more than 5% of your population. So say that my population is 20,000 and I'm doing, I'm only going to choose 10 people. Okay, do I need to treat, even if they are dependent, can I treat them as independent? And the answer is yes. When you have a sample that is no more than 5% of the size of your population, you can treat them as independent, which is kind of nice, especially if you have, like, you're talking about a company with 100 million employees, then yes, you'll be able to treat randomly choosing 4 employees as independent events, because in the grand scheme of things, making them dependent won't actually change your calculations all that much, and that'll help us avoid some very cumbersome calculations in the process. There are some methods for finding binomial probabilities. There is a formula, which is rather nice, and I really want to break it down in the next slide, so just bear with me here. So probabilities, we need to find the combinations of that number of successes. So that's where that comes in, and then we multiply it by the number of successes raised to that power times the number of failures raised to the number of failures that we would get. So this kind of like leads it all out. But let me go to the next slide, because that really explains what's going on. So this first part explains the number of outcomes that could happen with exactly X successes among those end trials. So that is our combination formula. So if you remember, so if you want to, you can just use, right? You can use your combinations from that we talked about in the previous chapter. So this is just, instead of writing that, let me just write this. This is combos. I'll just write combos. So you can use combinations, the combination formula here. And then this is going to be the probability part. So for each outcome, it's going to be that probability. And we have to count each of those outcomes together. So we need to find how many there are, but they all should have the same probability. So let's get back to that cashless example. All right, so they wanted us to find the probability that exactly 2 are cashless. Okay, so we're going to use that formula from the last slide, and we're just going to plug everything in. So we had 10 trials. So 10 factorial goes up here. Down here would be 10 minus 2 factorial times 2 factorial. And then multiply that by our successes. And how many successes do we want? We want 2. And our failures, and if we had 2 successes, that means there's 8 failures. So that is what we're going to put into our calculator. Very important. Now you can, if you're really savvy with your calculator, you should know how to do the combinations, and that is going to give you 45. So you would just do 45 times, and then 0.05 raised to the 2nd power times 0.95 raised to the 8th power, and do that all at once in your calculator. I'm telling you, it's the easiest way to do it is just to put it all in there all at once. Get comfortable with your technology. All right, multiply that all together. We're going to round to 3 significant digits. It's going to be 0.0746. There's our 3 significant digits, 746. So the probability that you're going to get 2 cashless adults when you randomly choose them out of 10 is going to be 7.46%. So not very large. Now that number may increase as time goes on, but for right now, based on the data, that's what we have. Now, you could use technology to find this answer rather than using the formula. So let me show you how that works. So if you can use StatCrunch, it will do this. Please make sure that you watch any extra videos that you need to about how to use your technology, because everybody's going to use a different technology and I can't name them all. So here's one that says if you use StatDisk, you can literally just tell it, this is what you have, right? The number of trials, the probabilities, and you can go right to the second line and it'll tell you the probability right there, right? Because we want 2 successes, it's that. If you want 2 or fewer, you would go to this line. If you want 2 or greater, you would go to this line. So it tells you everything you need to know. Mini tab, same thing. It'll actually make the probability distribution for you. You can just go right there. If you're using Excel, which is very similar to StatCrunch, again, you would go to 2 and there's your probability. If you're using a graphing calculator, same thing. You would go to the probability distribution and you would just go right to the number 2. So it just depends on what you're using technology-wise. Just know that technology is going to be a lot more, it's going to give you a lot more significant digits. So that, just keep that in mind. And when we start using charts and stuff, it might not give you the accuracy that technology would. It'll still be valid, but you might be able to get a little bit more accuracy when you're using technology. All right, football. Okay, between 1974 and 2011, there were 460 NFL games that were decided in overtime, and 252 of them were won by the team that won the overtime coin toss. Is the result of 252 wins in 460 games equivalent to random chance, or is 252 wins considered significantly high? All right, so we can answer this question by finding the probability of 252 wins or more in those 460 games. Now, again, we're going to have to walk through. This is another example where using technology would be a great idea, because it's going to, do things a lot faster for us than if we use the formula. So this is, anytime you've got a lot of, n's, your n is high, this would be a great time for. So our n in this case is 460. So this might be a little bit too much for our scientific calculator to handle. So just know that might be something you look at. Right now we're going to assume that the probabilities are the same for winning or losing. Now, that if we find that is wrong, then that's okay, but we should do that. And we are looking for the probability that 252 wins or more. So we want 252, 253, 254, all of those, all the way up to 460. Again, this is where using that formula is not going to be practical, because you'd have to do the formula for each of these numbers and then add them all together, which would take you forever on paper. So using the formula is not going to be practical. There is a table of binomial probabilities in your book, but the table doesn't go up to 460. So that would not be a good choice either. So technology here is really going to be the only solution. So let me show you. So if you're running StatDisk, or, again, StatCrunch will do the same thing for you. Every little, if Excel, all this will do the same thing. But you would go down to your list of 252, and then this one actually lists 8 or greater, so you can just go to this column and that'll automatically tell you your answer, which is 0.022 4289. I know it's kind of tiny there, but that's important. Okay, and our table in this, the table in the book is not going to help us with this one. I already mentioned that, because it doesn't go up to that high of an n. The one in our book only goes up to 8, n of 8. So as long as n is 8 or less, then you can use the chart that's in the book. Anyway, so I digress. So again, there are going to be times when your n is very large. You're definitely going to want to use some technology to help you out. But let me give you an example where you could actually just use the table that's in your book. So I just kind of screenshotted the table that's in your book. And we're going to go through this example and use the table that's in our book. So based on a Gallup poll, 5% of adults are vegetarians. If we randomly select 5 adults, find the probability, using the table, so here's the table, the probability that exactly 2 of them are vegetarians. Okay, so the first thing you have to do is use your probability here. So our probability was 5%, so we have to use this column right here, that's 5%. It says we want to find the fact that there are exactly 2. But first we have to know our n. And our n is 5 adults. So we're going to go down to 5 adults, which is right here. And we want to know the probability that exactly 2. Okay, so here are 2. So exactly 2 out of the 5 would be this little number right here. Okay, so that would be the probability. So the probability that we get 2 out of the 5 is going to be 0.021. So charts make it really easy, because all you have to do is know how to read them and you're good to go. Okay, then it says the probability that there are fewer than 3 vegetarians. Now, if there are fewer than 3, that means it's the probability of 0, probability of 1, and probability of 2, right? Because that's fewer than 3. So 0, 1, and 2. So all you'd have to do is just add up, you just go to here and add up your 3 numbers. So probability of 0 is 0.774 plus probability of 1 would be 0.204 plus the probability of 2, which we just talked about. Add those all together and you go 0.999. So you almost have 100% chance that fewer than 3 are going to be vegetarians. Almost 100%. Pretty close. Anyway, so that's charts are great, again, when your n is small. So definitely use those charts if the n is small. There are some other formulas that could help you. If you're trying to find the mean of a binomial distribution, you're just going to take your n times your successes. Very simple. If you want to find the variance, it's just n times p times q. And if you want to find the standard deviation, it's just the square root of that, and the square root of n times p times q. Great thing to use. Make sure you know these formulas because they are going to be helpful. Rule of thumb still holds for range. Still 2 standard deviations in either direction will be considered significant. If you are less than 2 standard deviations away from the mean, you are not considered significant. So that's the same rule that we've seen over and over again. All right, so if we go back to that previous example with the overtime, even though we couldn't use the probability distribution formula to find anything, we can find the mean and the standard deviation and all of that from this information. So find the mean and standard deviation. So here we go. The mean, again, all you do is multiply the n times the p. So in this case, n was 460, and we multiply that by the probability, which is 0.5. So our mean is going to be 230 games. Pretty straightforward. Standard deviation is just going to be the square root of n times p times q. So square root of 460 times 0.5 times 0.5. And again, just put that all in your calculator, and then make sure you go to enough significant digits. Okay, so there is our standard deviation is 10 games. So is that 252 game win that we talked to, is that going to be something that's significant? So let's talk about that. So use this rule of thumb that we just talked about to find that. So we got to go 2 standard deviations from the mean. So if we go on the low end, that's 230 is our mean, and we're going to subtract 2 standard deviations. And that would be 208, oops, 208. Sorry, that was very sloppy. Let me erase that. Try that again. Sometimes my writing gets sloppy on the computer screen. 208.6 games. So if there were less than 208 games, then that would be considered significant. And on the high end, we're going to add 2 standard deviations, and that's going to be 251.4 games. All right, so anything above that would be significant. So if we think back to our original problem, okay, right, that we had at the beginning, it said that is the result 252 wins significant. And it actually is, because if you look back at the last slide, here was our upper, right? Anything more than 251.4 games would be considered significant. So since 252 is larger than 251.4, then 252 wins is considered a significant amount. If it was 251, it wouldn't be, but 252 is considered significant based on that rule of thumb. So just again, we can just walk through those formulas and use them. So just to sum up, remember that X is significantly high if the probability of that, so we have a very small chance of winning 252 in overtime. And if it's considered significantly low, it would be less than 5% chance of that or fewer happening. So again, this is the same slide we had in a previous lesson. So go do some practice, and I'll see you in the next one.